Okay, so any questions on what we have seen so far?
No.
Okay, did somebody else join in?
Hi, sir.
Uh,
My name is Vignesh.
Vignesh, this is a Verilog training. Are you in the right program?
Sir, I just got this uh, mail, yeah, to join it. So,
Okay,
oh, sorry, yeah.
so you are looking to take Verilog training. Is it correct?
No, sir. Actually, I'm looking for Katia.
For Katia?
Yeah, yes, sir.
Yeah, this is not the one in that case. This is a different
Okay, okay,
training.
okay,
Yeah,
okay. Thank you so much, sir. Thank
yeah,
you. Yeah.
sure. So let me go back. Yeah, so any questions on whatever we have seen so far? Any doubts, any questions?
Hello. None from me.
Okay, no questions. Okay, so today we are going to look at briefly what FPGAs are and how they play a role in VLSI design and where Verilog comes into picture for FPGA or ASIC design for that matter. Just an overview of it so you understand the bigger picture, how Verilog will be used later on for design purpose, design and verification. So semiconductors, as you know, is pretty much everywhere. You'll find microchips everywhere in every domain nowadays. It could be telephony, it could be computing, aerospace. Lot of FPGAs and ASICs are used. Automotive space. Traditionally, it has been an embedded market, but nowadays you'll find a lot more FPGAs, especially FPGAs, coming into the automotive space for various purposes, especially connected networks. So you might have, especially in US, you might have seen Google cars moving around, automated driving driven cars, and there is a vehicular network that every all the cars should ideally communicate with each other over that network, and there is a lot of software and hardware that goes into it, where you'll find a lot of FPGAs coming into picture. So signal processing, image processing, and those applications, and some other applications. So you'll find semiconductors everywhere in the market today. So how does it all work? To design an integrated circuit, that's what a IC is. We need a lot of things. We need design services. That's where people come in, engineers come in. Then not everything is done by hand nowadays. So you have something called IP cores, which are like small designs, libraries of such IP cores, and libraries of special blocks that can be reused in your design. There's a lot of software that goes into it, additional software. There could be a OS involved, and there is a manufacturing part. So there is a lot of software and steps involved from a manufacturing perspective, processing, packaging the chip, and all to make it all happen. We have something called EDA tools. EDA stands for Electronic Design Automation Tools. So that's what EDA tools. These are basically softwares which are used to do design, library design, overall design. There could be IP core blocks. There could be other softwares involved for verification, embedded related softwares, etc. All of this is part of EDA tools, and then the actual design services part. All of this put together, you will create and design a chip and manufacture it. Once the chip is manufactured, you will send it to system manufacturers where it will be integrated along with the rest of the product or the rest of the system, and then it will be shipped to the end market, where the end consumer would use it. So this more or less is true. This is the logistics flow for any integrated circuit, and this is more or less true for any IC design that you will carry out from a overall perspective. So that's what it is. So we'll look at FPGAs. What FPGAs are? FPGA stands for field programmable gate array. So it's a blank slate for your digital hardware system. So what it is basically a blank chip given to you, and you can design any logic on it. So it's a programmable chip. So you can program it for various designs. So you can design, let's say right now I'm designing a processor and I implement that on a FPGA system. So the FPGA will start acting as a processor along with the rest of the system. Later on, I might develop some communication protocol. So what I will do is I'll erase the FPGA and reprogram it to make it work as a communication protocol device. Later on, it could be used for some other application like a set-top box and other things. So it is programmable. Earlier at the start, it's blank. You can implement any design on it, given you understand what we're doing. So FPGAs, to put them in context with respect to microcontrollers or microprocessors for that matter. Now, microprocessors are slightly older. Microcontroller is something that you can compare it to, because microprocessor is part of microcontroller. Processor is part of controllers. So when you consider an embedded microcontroller, what it will do is it will execute a program, normally a C program that's written for the microcontroller. There are fixed hardware and interconnections inside the microcontroller. So you have fixed number of ADC, DAC blocks, timers, interrupts, program memory, data memory, etc. So there is a fixed hardware inside the microcontroller, and it is interconnected. And all you can really do is write a program to configure all that hardware and make it use as per your logic. So that's what a microcontroller does. Now you compare FPGA with a full custom IC or a ASIC device. ASIC stands for application specific ICs integrated circuit. And ASIC are two types of ASIC, full custom and semi custom. So what full custom ASIC or full custom IC design is, basically you are designing right at the transistor level, which is the most basic building block of any IC. That's a CMOS transistor we're talking about. So most of these designs are a lot of it is analog design, which is happening at CMOS level, and some other digital logic design where performance is extremely critical. So in such cases, the design is done at a transistor level, CMOS transistor level. That's called a full custom ASIC or a full custom IC design. Then you have something called semi-custom IC design or semi-custom ASIC design. They are using standard cell, means standard libraries. Libraries are given to you. So we don't work, the designer doesn't work at CMOS transistor level, rather the designer works at a library cell level. So cells or components of the libraries are used to build your design. And then traditionally this PLD was part of semi-custom, but PLD is a new category for a while now. PLD stands for programmable logic devices. So CPLD was an FPGA. So CPLD was it's a much smaller version of the FPGA. The overall, I mean, number of pins is less. The capacity of the FPGA or the CPLD is less compared to a FPGA and some other things. So CPLD is a much smaller version of a FPGA, and FPGA is much bigger version of. But they are both programmable, and both can be programmed or designed using Verilog as a design language. So CPLDs are still used a lot. So the automotive space that we saw in one of the earlier slides, that's where CPLDs are used a lot more. In addition to microcontrollers, embedded microcontrollers is where automotive is dominated by microcontrollers, but nowadays CPLDs are used along with microcontrollers for other design purpose. So CPLD and FPGA fall under PLD category, programmable logic devices category. Say if you take a FPGA, it could looks a development environment for a FPGA could be as simple as this. You have a laptop which can be carried anywhere, or a desktop, doesn't matter, and a cable is connected to your FPGA board. So you can design something and test it on a FPGA board, and then if you are an engineer, you send out the block or the source code, Verilog code, for somebody else to integrate it in their design. Or if you're doing the entire design, then you can test it on the board directly, what it is. Obviously, this is a very simple version. This doesn't look like this all the time. This is, if you can see here, this is a card which goes on the motherboard. So this is very routinely done. This is a PCI interface. So this card goes on a motherboard inside a server, and you can have such racks, multiple racks of FPGA cards, and such multiple servers, creating something called a server farm, right? So, to give you a perspective of where FPGAs are used nowadays, now Microsoft is using FPGAs, or Facebook, or even Google is using FPGAs. Where are they using FPGAs? One application nowadays is when you type some, let's take Google or Microsoft Google search engine or a Microsoft Bing search engine. When you type something in the window, it will return certain results to you. Now, traditionally, these results were executed on a software-based servers, where it was all software in the background. Nowadays, that search is carried out. Part of that search is carried out on a FPGA platform in the at a hardware level. So why is it done? Because it will save some time. So let's say you save even zero point 0.1 second per search. If you even do, if you can even manage that zero point 0.1 saving zero point 0.1 second per search, there are millions and millions of searches happening every day throughout the world with companies like Facebook or Microsoft or Google. So imagine how much time can be saved. And since the time is saved, power is also saved, which is a very big factor nowadays. So power, there will be a lot of power efficiency that will come into picture if you can execute some of that search on a FPGA based device. So that's happening very routinely now. So that is just one of the new applications where FPGAs are used. So you'll see that that's why you will find this on motherboards in servers and server farms having FPGAs on. That's where FPGAs are used. So when to use an FPGA, right? So this question comes: when do I use a FPGA? When should I use a ASIC design, application specific IC design? So obviously economics is very important. Money comes into picture, so it's one of the most important things. Using FPGA, we have the shortest time to market. So the overall design cycle for FPGA is much shorter than a design cycle for ASIC device. For ASICs, there is a lot of stuff involved in the backend part of it, not the Verilog part, but the backend part where a lot of manufacturing related activities. You have to do a lot of checks and some additional steps from a manufacturing perspective before the design is sent out for manufacturing for ASIC devices. FPGAs are pre-built chips. You can directly buy them from the market. They are blank chips. You can buy a standard board also, as we saw here. These boards, similar boards are available in the market. You can use them directly in your engineering environment, or you can custom build them. But overall design cycle is much shorter. Since the design cycle is smaller, the NRE cost is lowest or lower side. NRE stands for non-recurrent engineering. Means it's a one-time engineering cost. So to design something, a team of engineers and other people are required. So it's a one-time cost used to which is required to design a particular product. Now, one of the problems with FPGAs till recently was the unit cost or cost per FPGA was on the higher side when you compare cost per ASIC. Now that difference has come down drastically because FPGAs are also manufactured and available in bulk quantities nowadays. So the cost per chip is has gone down. This was true till very recently, that maybe till 10 years ago. Quick grab of market share and then do the cost reduction with ASIC. So what people used to do, or what companies used to do, they used to design new products with FPGAs in them. And since FPGA used to take lesser time to design compared to ASICs, so and they would launch these products in the market. Once customers liked the product and they were used to having that product, then they could reduce the cost of the product or offer more features in the same cost with ASICs, because ASICs takes more time to design. But once you design the ASIC, you can manufacture that ASIC in bulks and bulks of quantities. So when you manufacture in bulk, the cost per chip goes down. That's how you can reduce the cost of the overall product. So do the prototyping and the initial launch of the product using FPGAs, and later on reduce the cost of the product or offer more features with ASIC design. That was a typical method. But nowadays, as I said, FPGAs can also be manufactured in bulk, and they are manufactured in bulk. So companies who want more number, so somebody who is selling a lot of volume, millions and millions of devices, they can get FPGAs at a much lesser rate compared to earlier. Very comparable to ASIC cost. One more reason to choose a FPGA is architecture driven, means depending on the type of application. So if you're working on any signal processing application, as I was talking about, or image processing application, FPGAs tend to work better compared to ASICs. ASICs can be designed for any logic, but FPGA, similar logic can be designed with the FPGA in much lesser time. Typically, signal processing applications, FFTs, fast Fourier transforms, digital filters, any multiplier or any arithmetic operations, FPGAs will give you better performance, and that too quickly. One of the problem areas was no area control. So that was another area, a problem area. The way FPGA works, it's a pre-built ready chip to be used. So either you use the entire chip or you use only 50% of the chip, doesn't matter. There is a term called board real estate. Board real estate means if you develop a PCB, printed circuit board, you will place a chip on the printed circuit board. So that chip will take certain area of the PCB. That's called board real estate. So that space will be, so whether you are using the entire FPGA chip or only 50% of it. If you're not using the entire FPGA chip, that means you're wasting the chip resource and you're wasting the board resource also. So ASICs on the other hand can be designed as per the design. You can reduce the size of the ASIC as required. So the chip is efficiency also goes high and the board efficiency also goes high. So that is one area where it's a negative. Limited power control was recently very true. Nowadays, FPGAs are developed with new softwares which give a designer more control over the power dissipation in the FPGA device. So we can have various methods where we can design a lower power version of the device of the design using FPGAs. And semi-custom, we will not go into details of it. Semi-customs, as we said, are developed using standard libraries or standard sets of libraries are given to a designer, and we can use those libraries. Full customs is mostly done from scratch at CMOS transistor level. When you work at CMOS transistor level, it will take a very long time to do any design. But it is justified when you need more performance. So it's like you're fine tuning every small section of your IC. That's what happens when you work at CMOS transistor level. You're fine tuning various sections. Obviously, it will take more time. More time means it will cost more because more engineers are required for longer time. So their cost and other costs goes up. Typically done for analog based designs. Analog designs are mostly done in CMOS transistor level design. Even for CMOS transistor level design, there is a language called SPICE. Maybe you guys have used it in one of your grad school projects or tasks somewhere. Right? So SPICE is another language which is used for analog design, which where you create a structure of gates and transistors to create a bigger design out of it. Memories are typically done at analog level using CMOS transistors. So that is full custom ASIC design. To put it in perspective, FPGA's semi-custom ASIC design, full custom ASIC design. Time to market, the quickest is FPGA. The worst is full custom. It will take a very long time to design a full custom ASIC device. Volume means it's a cost per chip. Nowadays, FPGAs and semi-custom ASIC are at the same level. Full custom ASIC will give you the best cost per chip. So when you require a very high volume of chips, then going full custom ASIC design is one of the best ways to reduce the cost of the chip. FPGAs and semi-custom ASIC, same level. So semi-custom ASICs are actually phased out nowadays, or mid-level ASICs are phased out and being replaced by FPGA designs, based designs. Performance also, FPGA based design and semi-custom ASIC design will give you very similar performance. But performance of full custom design, basic design will be the best because it's really fine tuned right at the CMOS transistor level. Depending on your constraints of your project, you can choose one of the chips and start designing using that. From a market application and a market share perspective, you'll be surprised a lot of FPGAs are used in military or defense, followed by aerospace design. So military or defense, you might have seen the Mars mission now and the last Mars mission also, the rover and the new one. They had a lot of FPGAs in them. Aerospace, you go to Airbus, you go to Boeing, you'll find a lot of FPGAs used in their aeroplane based inside the aeroplane and even other related activities. Telecom is a big market. You will find a lot of routers and switches which are used for your broadband purpose. The routers and switches will have FPGAs in them. Automotive market is catching up with CPLDs and bigger FPGAs. Industrial automation is a very small market. It's traditionally dominated by the other electronic solutions like PLC and some other things which have been still used. This is a slightly older. I need to update this slide. Xilinx is the number one FPGA vendor. Altera, which was recently purchased 3 or 4 years ago by Intel, so now this is Intel. So Intel has a microprocessor and Intel also has a FPGA device now. And they have recently come out with a device which internally on the same device or on the same die, they have the processor and the FPGA interconnected to each other. And the processor can be programmed separately and the FPGA can be programmed separately. So that's the number two vendor for FPGAs. Lattice Semiconductor has been around for a while. That's very small but still around. It's number three. Xilinx was recently there has been actually a merger happening. Actually, it's an acquisition in a way. Xilinx is getting acquired by AMD. So now very soon, it's the whole thing is in the process. So now it will be Xilinx and AMD together, just like Intel and Altera have combined processor and FPGA logic. AMD processors will be combined with Xilinx FPGAs, and they will offer a combined solution very shortly. So that's it. That's happening right now. These are mostly the three vendors who offer you FPGAs. Yeah, so this is just the internal architecture of the FPGA. We will probably skip this the time. Okay. Uh, so FPGAs internally are made up of something called CLBs, called configurable logic blocks. This is where all your logic that you are declaring in Verilog will go into this configurable logic block, which are internally lookup tables or memories basically. Lookup table is like a memory. So all the logic will be implemented in a CLB and ultimately inside a LUT. And it has CLB has LUTs and some flip flops and other stuff. Then the next part is interconnect. So all these configurable logic blocks are interconnected with each other using programmable interconnect. So you can define now if the logic in this block needs to communicate with the logic in this block. So this interconnect will be active. So it will communicate like this with this block. If the logic in this block has to communicate with somewhere here, the appropriate interconnects will be on and this logic will communicate with this logic here. So these are interconnects which can be programmed as per your design. There are some special blocks in the FPGA, PLLs and DCMs. DCM stands for Digital Clock Manager. So clock is very important, as you might have studied earlier. Clock is one of the signals that is routed throughout the chip. So you have to have clock with very minimum skew or distribution delay. Then you might need special clocks in your design. So the incoming clock has to be maybe you need special clocks in your design, like 2x the incoming clock or 4x the incoming clock, or a phase shifted clock by 90 degrees or 180 degrees or whatever. So this is offered by the standard block inside the FPGA. So you don't have to write the separate logic for it. You can directly use this block, which is a special block of FPGA, and you can get the special clocks which are generated and then use it for your design purpose. So clocks are very important, and that is supported by this block and similar other blocks. IOs. So there are input output blocks on all four sides of the FPGA. The input output blocks can also be programmed. All the pins can be input or output depending on what your requirement is. And the input output blocks can support voltage levels, various voltage level like TTL, CMOS 3.3, CMOS 2.5, and it nowadays up to 1 point, right down up to 1.2 volts. So the IOs work on those voltage levels. We have some special IOs which are very high speed IOs, which are used for high speed communication purpose with the server side in case it's required. There are special blocks inside the FPGA for special memories inside the FPGA which act as a on-chip memory. And there are other special blocks used for special applications like multiplier, which is used for signal processing application and other stuff. So there are some special blocks inside the FPGA. Way it works is you write a Verilog for this. Now this is the circuit given to you, digital logic circuit given to you. You'll write Verilog for this, and ultimately it will get converted to a CLB and a LUT inside the FPGA. Here, I'll have a better slide here somewhere. And this is just a programmable interconnect that you will see. Yeah, so if you this is a cross section of the FPGA. These are inputs and these are outputs here. So a logical path will look something like this. The input is going to some logic here. Then this logic is inside this CLB configurable logic block. Then it is talking, communicating with some other logic in this CLB block. Then it is through this interconnect. It is going to the output here. So this is the path from input to output, and there are thousands and thousands of such paths all across the device. This is a typical flow, a design methodology as we call for Xilinx FPGAs. It is also true for Intel FPGAs, and it will also be true mostly for all ASICs. Before we start writing Verilog for anything, before this step we do something called design specifications. So we have to, somebody does it, uh, normally a team of architects, software and hardware architects will do that. They will decide what needs to be designed. So that all that is put into a document called a design specification document. Once the design specification is done, then they would partition the design. They will decide what needs to be implemented as hardware, what needs to be implemented as software. Once that is defined, then the hardware part is where VLSI design comes into picture. So under hardware, some part will be implemented on a board level using PCBs, custom made PCBs. And some part will be implemented using chips. The part which needs to be implemented as a chip will come here as a design specification for that. Then you or a team of engineers will start writing Verilog code for that. So let's say you are given a small block to design. For that block, you know what needs to be implemented for that block. There is a very clear document that talks about that. You will start writing Verilog code for it. Now, once you write the Verilog code for that block, you need to test whatever you have designed here. So for that, you need something called a test bench. A test bench is also a Verilog file. Now this Verilog, the design will be in Verilog and the test bench will also be in Verilog, and you will use this test bench to test your design. And you do something called simulation. So after simulation, you'll generate timing diagrams. The timing diagrams will tell you whether your design is working correctly or not. If it is not working correctly, then you have to fix your design. And this is the iterative process. So you keep doing this till your design is working as per this design specification document, because that's a reference that you're following. Once that is done, once your design is working as per the design specification document, you say that my functional verification is done or my design is functionally verified. Means the functionality of the design is correct. So once that is done, then you need to take the design forward. The test bench is kept here. You take the design forward because now you want to implement that design on a FPGA chip which is on this board somewhere. So you need to convert that Verilog code into that format. So Verilog is then synthesized. This Verilog code will get synthesized or converted to netlist format. Then it goes and follows certain other steps called mapping, which is then using the this netlist is in generic gates, basic gates. Then it is translated or converted to Xilinx FPGA or any other FPGA or ASIC devices. The components from that library, they are placed all across the chip, and the interconnections between all the components are done, which is part of placement and routing. You do something called static timing analysis here afterwards to make sure all the timings which you are setting here. You can set, for example, a clock. You can tell the synthesis tool that this logic that I have developed needs to work at 100 megahertz, for example. So this report will tell you whether all the paths in the design are working at 100 megahertz. So there is a report that you have to read, and if there is a problem, you have to fix the problems there. Then you do something called bit file generation. Now, bit file generation is a file that is used to program the FPGA. Then you program the FPGA, and the FPGA will be on the board. So this board and the FPGA on it will start acting like this design that you have created in Verilog. So all of this has to be done for FPGAs or ASICs. For ASICs, there are some additional steps which are required here to make sure that the manufacturing part is done correctly. So FPGAs, this is the standard flow. Even though this looks like a smaller part, now if you consider the entire design cycle, now this is the entire design cycle from design specification, document creation to working FPGA or a working chip on the board. This is the entire cycle. Out of the entire cycle, around 60%, 60% of the time will be spent in design and verification. 60 to 65% time will be spent in design and verification. Other 30, 35, 40% of the time will be spent on the back-end activity. Synthesis onwards is called back-end activity. Synthesis is sometimes merged here and here, both sides. It's called RTL synthesis on this side, called physical synthesis on this side. So it partitioned, and half of this it goes here, half of it goes here. But typically synthesis and everything onwards is part of back-end activity, and this is part of front-end activity, where you will write Verilog code for your design specification, test your Verilog code, simulate it, generate timing diagrams and other reports, and check whether everything is working correctly as per the design specification or not. If not, you have to fix it. These steps take around 60% of the time, and the other steps take lesser time because they are mostly automated using software, specialized software, EDA tools, as we have seen. Any question on this flow? Do you understand this, and any questions on this?
None from me.
So if you understand now, if you look at the bigger picture, do you understand where Verilog comes into picture and why you have to write something in Verilog?
Yeah.
Right, so we'll start looking at shortly, we'll start looking at Verilog in detail, but that's where Verilog comes into picture, and you need to be good at that. So we will start learning Verilog later. Yeah, this is the way FPGAs internally the chips are tested. There are various FPGAs designed by Xilinx and Altera, which is Intel. We already saw this. Yeah, so one thing we will see in Verilog is a digital logic circuit can be represented in these various formats. The bottommost format is the transistor level, which is CMOS level. So you can design your chip at a CMOS level and implement it. Or now the structural and gate level are combined. Now this is called, we call it structural level, where we create a structure of design. So using basic gates and some other blocks, but we will create or we'll write a Verilog code directly using those blocks and using those gates with all the interconnections in between manually done in Verilog language. That's called structural design. And then we have something called behavioral design, where if I say C is equal to A plus B in Verilog, that will implement the adder for me because I'm saying A plus B. So that is a behavioral way of defining Verilog. So in Verilog, we have two levels: behavioral level method of designing and structural level method of design. Transistor level is not done in Verilog, that's done in CMOS, which is analog design. Digital logic design can be represented in structural or behavioral format. It's called top down or it's called bottom up. Normally, when you design very big chips, you will end up using both behavioral and structural methods for design. So when you design something, you should consider design style. So as we just saw, structural or behavioral method or style of design. You should consider designing for an architecture. So you have to look at the application that you're trying to develop. Depending on what kind of application it is, there are special ways to design it. Investigate the tool output. So there are lots of software used, which are called EDA tools. You have to look at the outputs and reports of each stage and see whether it is working correctly or not. And if not, then you have to fix it. Know how a synthesizer thinks or works. So synthesis is a very critical part of this entire flow, which will convert your Verilog code to netlist format. So depending on how you define your Verilog code or Verilog design, the synthesis tool will automatically convert that to netlist. So you have to understand when you write something in Verilog, what will be generated in hardware, because that's what the synthesis tool will do for you. So you have to understand that. We'll see that when we see Verilog section, and understand it as well as you can. So that way, because ultimately, Verilog is just a means to the end, right? Ultimately, it's the working hardware that you will be working with, or some other team will be working with. Verilog is just a way to get it done. So understanding how synthesis works is also very important. So why do we need HDLs? Can anybody answer that? Have you guys done schematic design before? Anybody?
Well, I think HDL is meant to kind of describe the logic of how the hardware should work.
Yes, but that can also be done using schematics, for example.
Yes, yes, that can be done using schematic. But I'm thinking, HDL is kind of as a language, so it's kind of a way of instead of diagrammatically representing the logic like in terms of gates and the wires, then the HDL kind of is a language like it just says this needs to do this, this needs to communicate with this. That's just what I think.
Yeah, yeah. So you're right that with HDLs, HDL stands for hardware description language. We are describing the hardware. That means it is much easy. It's a language. So we are when you design something using a language, it's much easier because the language, once you follow that language, it's much easier to design. Schematics is like manual design. You take gates, you take components, you connect something to the input, connect something to the output, and you keep doing it for thousands and thousands or maybe millions of gates, which will take a very long time. So before HDLs came into picture, engineers used to design chips using schematics, which was taking very long time. So to design one chip on an average, they used to take anywhere between 3 to 5 years, which was once HDL came into picture, it was reduced down to 1.5 2 years. And nowadays, a chip is the term uses we are taping out a chip, means we are designing and finally the manufacturing was also done around 6 to 8 months time. That's typically the time that new designs are pushed out in the market. So we can design the complex chips very relatively very faster compared to the earlier methods of schematic design. So HDL can describe both the circuit structure and the behavior. Circuit structure means the connections between components and blocks. Schematics, lot of focus was on the structure. The behavior part was tested later on. Whereas with C language, now why not use one of the existing languages, like something like C language, which has been around forever? So we'll see what is the difference between C language and any HDL for that matter. So C language will mostly help you describe the behavior, not the structure. Uh, doesn't allow you to do that in a standard C language. When you compare HDL with schematics, it provides you a higher level of abstraction to speed up the design. So, as we were just discussing, using a language, we can quickly describe the behavior of our digital circuit, and the synthesis tools and the other backend tools will then convert it to the hardware automatically and quickly. Schematic design, everything was done manually. Most of it was done manually. So it takes a longer time, and it manual means more longer. This language means a higher level of abstraction. You have a level of abstraction that can be used to speed up your design. Higher portability and readability. Now, Verilog designs, and there is another language called VHDL. So Verilog or VHDL designs are portable, means you can take it, use a block of Verilog design in some other design. You can integrate this block into some other design. So they are highly portable and readable. So it's a language, so you can read it and try to understand what is really going on from a logic perspective. It enables rapid prototyping. Prototyping means we are creating samples or smaller models of our product or of our system. So we can quickly design using Verilog method, quickly design, implement it on a FPGA or some programmable device, build a small model of our system and test it, whether the system is working as per the expectations or not. If it is not, then we try to analyze where things are going wrong and we try to fix it. So that's prototyping. It supports different hardware styles. So we have seen structural style, we have seen behavioral style, and then we will also see some special methods. So Verilog as a language can support some of these things, where schematic it was difficult to do that. That is some of the reasons why we need HDL languages compared to schematics. So what do we need from HDL? HDL, first of all, HDL is used for hardware design. It is the full form of HDL is hardware description language. So we are using it to design hardware, that to digital logic hardware. So anything that is part of digital logic design, the Verilog language or VHDL should support it as a hardware language. So we should be able to design combinational logic, level sensitive storage devices if required, edge triggered storage devices, sequential logic, then we can add FSMs to this, memories, etc. Anything that is part of digital logic design, the HDL should be able to help us design that. And we can design it at various level of abstractions. So these two are combined at a transistor level, CMOS level. Gate and structural level is the same thing. RTL level is behavioral level. And nowadays, people are trying to go one level above Verilog, which is called system level design. So right now, Verilog as a language or VHDL as a language doesn't support system level design. So I cannot just tell it that implement the encryption logic and that's it. It will implement everything for me. So there are certain proprietary tools who does some of that, but not maybe the entire thing. So there are blocks which can be used, and those blocks, the code, the Verilog code is automatically generated for that block. But that works only for simple designs and very small blocks, not very big designs. So there is effort going on right now where we can go one level above Verilog and implement something at a system level to make the design part even more easy. So we went from transistor to gate level in Verilog, from gate level to behavioral level, which is also called RTL level. Now we are trying to go to system level, but that will take a little bit more time to get to that point. So that's what the different levels of abstractions are. One of the key things now, I think Brolin, you have done embedded design, right? So what is, or my question is open to everybody. So what is the key difference between the embedded program and hardware design, or a C program? Rather, let's go back and say it's a software C language C program and a hardware design. Key difference between both.
C would be behavioral and
Your voice is breaking up. Can you speak up a little bit?
C
Hello.
design would be behavioral.
No, I didn't get it properly. Sorry. Hello.
Key design would be behavioral.
VHDL or Verilog doesn't matter. When you are designing with let's take Verilog because we are considering Verilog as a hardware design language. So what's the key difference? Rather than just comparing languages, what is the key difference between a software program? Let me put it that way. What is the key difference between a software program and a hardware design? The way it works.
So software programs work with in sequential manner, like they
Okay.
are executed in top-down fashion, and Verilog is executed in parallel manner.
Yes, so that's exactly correct. That software program doesn't matter whether it's a very small 10 line program or a very, very long program. It will work sequentially one after another. Whereas when you consider hardware design, it can be designed using Verilog or any other language for that matter. It has to support parallel execution or concurrency as it is called. Concurrent execution of logic means parallel execution of logic. So hardware has to support that because that's how hardware works. Let's say there are four inputs to your product. Let's say there is some box and there are four inputs. Based on the four inputs, some decision has to be taken. Maybe first input triggers a alarm, second input triggers something else, a motor control, something like that. So it can happen that all four inputs can come at a time. Maybe one of the inputs come at a time, or any combination of inputs can come at a time. But parallel execution has to be supported for hardware design, not necessary for software. So typically, traditionally, software has been sequential execution. Now they're trying to change that. There is a lot of parallel computing efforts going on, etc. But it's very specialized and it's not really in main domain yet, where they can people are trying to use nowadays. Now, if you take a smartphone, for example, your smartphone processor internally has a quad core process. It will they'll display that there is a quad core processor or a octa core processor. That means the single processor chip will have four processor cores inside it for quad core. For octa core, it will be eight cores, processor cores inside the single chip. So now it is the software team's responsibility to figure out how to use these four cores at the same time or eight cores at the same time to make the software execution more efficient. So it's happening slowly, but it will take more time. Traditionally, software is sequential execution, hardware is parallel execution. Since we are using Verilog for hardware design, it has to support this parallel execution part. And we'll see later on how it supports that. This is a flow that we saw uh, along with parallel execution. And there is one more key thing that is different for software programming and versus hardware design is the timing control part of it. So we can control we have to control a lot of things at a clock cycle level in hardware, or we need precise control over hardware from a timing perspective. So that is not so much true from a software perspective. It is not so strict, and it is basically left it to the compiler and other tools to manage some of that. It is very less control is given to the user to control it at a C language or any language level. Whereas in hardware, I was just giving an example of four inputs. Now, this if this four input comes are active at the same time, how do you resolve this? There has to be certain priorities given. Now the priorities also, maybe might be some timing issues involved between them. Which is coming first? Which is coming second? Or what is the difference? How it works? So everything has there is a lot of critical timing control that has to be done in hardware design, which may not be necessary in software programming, and which may not be possible also to a certain extent. So those are the two critical points which are differences between software programming and hardware is the timing control part of it and the parallel execution part of it. Where that's why you need a separate language for hardware design. This is also the same block diagram that we just saw for FPGAs, so I'll skip that unless you have a question. So to make it happen now, there were two hardware description languages that were developed. Verilog came actually later on, though Verilog is more popular now. Earlier, VHDL was a language which was developed. Now, this was developed based along the lines of a software language called ADA, which is also still around in very critical systems. And this ADA was developed by US Department of Defense because they have developed this language. And even VHDL was developed by them for internal design purpose, and it was then released to the engineering community. So VHDL, all these both languages were developed by them and then released. VHDL is called a tightly typed language. So there is a very strict rules in doing VHDL design, how it is designed and how it is implemented. Then later on Verilog. Verilog was a private language, a proprietary language earlier, was developed by one of the companies. And then that language became popular, and then after it became popular, it was opened up as an open source language for the entire engineering community. Now this language, the syntax of this language is very close to C language. So it is, and obviously it's much more flexible due to that. So flexible and easy to use. That's why this language has become more and more popular over the last maybe 15-20 years. But anything, they are equally effective. So anything that you can do with VHDL can be done with Verilog and vice versa. So it's not that we can do certain things with one language and cannot do certain things with other language. Verilog, one more difference is that VHDL till very recently was more Europe centric. So most of the Europe was using VHDL, and Verilog was mostly North American centric. So mostly US and some parts of Canada was where Verilog was used. Nowadays, Verilog has the popularity has grown. So Verilog is the language of choice. VHDL is still used in some parts of Europe and even some parts of US, some companies rather, but that has slightly fallen back. And VHDL is the language of choice for academic research purpose. So if you go to any universities, they'll prefer VHDL. Most of them will prefer VHDL compared to Verilog. That's just it's working. But Verilog is where all there's a lot of action happening in Verilog since last long time now. So yeah, so that's what we looked at. We looked at some of the introduction to VLSI chips, architecture for FPGAs, design flow, design styles. Why do we need something like a hardware description language, and what do we need from hardware description languages? Any questions on any of this that we saw?
No.
No? Okay.
Not from me.
Okay. So since we have few more minutes, I will start the next section. I was not planning to, but anyway, so we have a few more minutes. Start looking at Verilog step by step. So till now, what we saw was we had an overview of digital logic design, basic gates, sequential circuits, combination circuits, memories, FSMs. Then we looked at number systems briefly. Then we looked at FPGA, where Verilog comes into picture for FPGA design or ASIC design for that matter, as part of IC design. So since now you understand where Verilog comes into or falls into the bigger picture, we will start looking at Verilog in detail, the syntax and other things, how to design digital circuits using Verilog. So HDL, as we just described, is stands for Hardware Description Language. It's a text-based method for describing hardware to a synthesis tool. So it's a language. So you use an editor to write a design, and that Verilog file or that Verilog design is the input to the synthesis tool or the synthesis software, which will then convert that Verilog design to gate level netlist. That's the first stage of hardware. The advantages of HDL that we have seen over schematic and some other methods is it produces correct designs in less amount of time. So in less amount of time we can create correct and much larger and complex systems in the same amount of time compared to schematics and other methods. the focus is shifted to specifying the functionality. So our focus is not interconnections as it was in schematics. The focus is on functionality. Is the functionality correct? Is the logic correct for my design? That's where the focus is with Verilog. The synthesis tool automate details of connecting gates and devices. So once the Verilog functionality is defined properly, then that is given as an input to the synthesis tool, which will then convert that design to gate level netlist, and the gates and the interconnection between gates of all that will be taken care automatically by the synthesis tool based on your Verilog design. So you save time on that. With the schematic based flow, this was a flow. Schematic, you draw or make a schematic. Netlist is created out of it. You can do a gate level, netlist level simulation and then implement. With HDL based flow, you write a Verilog code for your design. Your design specification is translated into Verilog. You write a test bench and perform simulation. As long as the design is not correct, we'll keep doing it. Once the design is correct, as per the functionality of the design is correct, we take that design, synthesize it, follow the backend part of it, and then finally implement it on the FPGA system. This flow is for HDL based flow or design, and this is for schematics. This overall will give you much more speed up in your design compared to the other flows. So some of the other advantage that we have already seen is we can operate a higher level of abstraction. So since we are using a language rather than schematics or manual connections, the level of abstraction is a level above. We can debug earlier. This is very key with a behavioral simulation. So once your design is ready, we can write a test bench and we can simulate our design to check whether there are errors in the design. If there are errors in the design, we will solve those errors right there and then, rather than those errors getting translated to the backend part, or even worse in the product where there could be errors. We have special methods for doing HDL design, something like parameterized design, which makes it easy to make wholesale or wide level modifications to the design. So for example, we can declare a parameter. Parameter is like a constant called bus width, and the bus width is the constant declared once, let's say 8 bits. So then I, rather than using 8 as a hard as a absolute number, I use this alias or this label called bus width throughout my design. In case I want to change my design from 8 bits to 16 bits, it's much easier for me because all I have to do is go and make a change at one place. Bus width will be equal to 16 instead of 8 bits. The rest of the places only label bus width is used. So it's much easier to make changes this way using parameterized design, and there are some other methods also which you'll see. We can quickly specify the desired behavior. Now, if I want to design an up counter with reset, what will be the small piece of Verilog code? It will look something like this. If reset equal to 1 means if check if reset is high. If reset is high, reset the counter. Counter gets 0. Else count gets count plus 1. So if reset is high, reset the counter, else count upwards. So this is a very small Verilog piece of code which is used for up counter with reset. We can focus our energies on specifying the functionality of the design rather than interconnections. Now this count signal could be 4 bits or 8 bits. If it is 4 bits, then once we synthesize the design, this counter will be implemented by using 4 flip-flops. If it is 8 bits, it will be implemented using 8 flip-flops. And all the interconnections between them will be done by the synthesis tool. You don't have to worry about how they are interconnected. Your focus as a designer is on the functionality of the design. Can target multiple devices. So this is also very key. This is it helps with the product migration or portability. So once we design something in Verilog, the same design can be used to implement a FPGA, and under FPGA you can implement it on a Xilinx FPGA or a Intel FPGA, or the same Verilog code or the Verilog design can be used to implement a ASIC later on, or at the same time sometimes it is done parallelly also. You don't have to write two different versions of Verilog code. As long as the Verilog that you've written is something called technology independent. What that means is, if you're writing your Verilog using just the Verilog language, at that point you are not using special blocks from the FPGA or special blocks from the ASIC library. If you are not using that, your Verilog is technology independent. Means it is not tied to any particular technology. It is general purpose Verilog. In that case, it can be used later on for different FPGAs or for ASIC devices. But for some reason, in your Verilog code, you have used some special block from a FPGA library, Xilinx FPGA library, like a multiplier or a memory or something. Then your Verilog code is tied to that particular FPGA device or FPGA vendor. Or your Verilog code is using some part of ASIC library, similar multipliers or some special component from one of the ASIC libraries. Then your Verilog code is tied to that particular ASIC device. Now, if you want to convert or use that Verilog code with a FPGA, you have to replace that component with a similar component from this library. But ultimately, you'll have to make a change here in the Verilog code. So it is no longer technology independent. It is dependent on a particular technology. So you should be able to write, or you should write Verilog code which is technology independent as far as possible. Very rarely you might end up using some blocks, but at that point you are sure that your product is going to use this particular FPGA or a particular ASIC library for that matter. ASICs libraries are also from different vendors. So you'll have all these different ASIC vendors. Now Intel is one of them, ST Micro is one of them, Samsung, whoever is manufacturing your device. Um, uh, then we have the Chinese guys. Who was that? I forgot. Global Foundries, right? So whoever is manufacturing your ASIC will offer you libraries for design purpose. And if you use any such block from those libraries, your design is tied to that ASIC vendor. Or if you use any block from Xilinx FPGA library or Intel FPGA library, your Verilog is tied to that particular FPGA device. So wherever possible, don't do that. In case it is required, you will end up doing that. But then you have to know that Verilog is not independent. There is a dependency on this family, this technology family. Any questions on this slide or any earlier slide?
No.
Okay,
No problem.
so I think we'll stop here today, and we will continue with the next slides on Monday, same time.
Sounds